Okay, so today we're going to talk about electric potential energy. Now, we've talked about potential energy a fair bit in grade 11 physics and again earlier in this semester. Potential energy is energy that is stored, like gravitational potential energy. So if you're on the roof of a building and you're holding an object out over the edge of the roof and someone says, does it have any gravitational potential energy? The test to see if it has stored energy, potential energy, is to release the object, and if it moves, it does. So if we were holding that object out over the roof of the building and we let it go, that object would fall. You'd be like, oh, look at that, it does have gravitational potential energy. Or if we stretch a spring, right, and we're holding it out stretched, and someone says, does it have any elastic potential energy? Well, we would figure that out again by releasing it, and as soon as we release it, the spring will move back in. Okay, so potential energy is energy that's stored in an object, and we can tell if it has potential energy by releasing the object, and if the object moves, then we know it does. So electric potential energy is exactly the same idea. So let's imagine we have a source, the source of our electric field, and we'll say it's a positive charge, okay? So our field lines, the same would work for a negative, I just picked a positive. So we have our field lines going out in all directions. If it was negative, they would be going in. Okay, so here are my field lines around my positive charge. And now let's suppose I have my Q2, my second charge out here. And I want to move this charge, this second charge, into the source. Okay, so I want to move it from wherever it is into where the source is. Well, these two charges don't like each other. And I'm going to be moving this second charge against the field. I'm going to have to do work on it to get it there. It's not going to go there by itself, right? I'm going to have to apply a force over some distance to move it into here, right? And so the result will be a change in energy. Remember from grade 11 physics, the work done will be equal to a change in energy. In this case, the change in energy will be EQ, delta EQ. So that means delta EQ, remember work is F delta D cos theta. Well, the F here is going to be FQ. The force I have to put on it will be equal to the force of repulsion that it would be feeling. So then delta EQ would be equal to K Q1 Q2 over R squared. And the delta D, the distance that I'm moving it, is really just the R. So it'll be times R. And the cos theta, well, if I'm putting an F on it, and I'm moving it this way, the cos theta should just be cos of 0. So that's going to go to 1. And one of the r's will cancel. And so the change in electric potential energy will be equal to K Q1 Q2 over R, because one of the R cancels with the squared. Now usually what we say is we're going to start this second charge so far out, infinitely far away, so that, because remember delta is final minus initial. So we're going to start it so far away that the initial would be 0. And then we would just be left with EQ is equal to K Q1 Q2 over R. Okay, so this is our equation for finding the electric potential energy between two charged objects. Remember, all of energy is a capital E with the subscript of telling us what type of energy it is. And so the Q is telling us it's electrical. Now, and also remember that energy is a scalar. So we don't have to worry about direction, which is a good thing. But you could have positive or negative EQ, right? If both Q's are positive, so both Q's positive, then EQ will be positive. And that means you have to do work to move the object, to move the second charge in, that it doesn't want to go there on its own. If both Q's are negative, the EQ will still be positive. And it still means you have to do work because the two negatives won't want to move closer together. But if one Q is positive and one Q negative, then the EQ is going to be negative. And when you get a negative EQ, it means the field does the work, not you. Right? So if I had a negative charge up here that I wanted to take in, I wouldn't have to do work. They're going to attract each other. It's going to go in on its own, right? And so the result then would get, but when I fill a positive and negative in here, I'll end up with a negative EQ, and that's telling me that the charge wanted to move there when it was released. Or I didn't have to do work to do it. Think of it like moving a positive in here is like taking a kid to the dentist, right? Not going to go on its own. So you put a force on it, you do work on it, more force, more force, more force. You finally get the kid to the dentist office. You set the kid's butt in the chair. You go up to the receptionist to say, we're here. So you release the kid, and what does the kid do? Zoop, goes right back out, right? So there's electric potential energy. When I move this positive charge in, doing work, forcing it in here, it gets to this point, and as soon as I release it, it moves back. So I'm doing positive work to get it here, and then negative work happens when it moves, meaning the field does the work to move it out. If it was a negative charge that I was trying to move in, then I wouldn't have to do any work at all. It would be like taking the kid to the candy shop or an ice cream store. You don't have to do any work to get the kid there. They go willingly. But when it's time to leave, you have to drag them kicking and screaming away, right? So I do positive work. The field is doing the work when it works out to be negative. And it simply means that the charges want to go together when it's negative, or they want to do whatever the question is doing when it's negative. Okay? So that's electric potential energy. Now, after we had figured that out eons ago, people began to say, but I'd kind of like to find, like, what's the potential energy at a spot in this field regardless of what charge I bring in? Like, I'd kind of like to know, like, how much energy is here in this point, even if I don't have a charge of 2 coulombs or 6 microcoulombs at that spot. I want to get rid of the charge that I'm bringing into the field. I want to take my EQ and I want to divide it by the charge brought into the field. Okay? So if you think of our equations, so we had FQ is equal to KQQ over R squared, and this is a vector. And then we divided out one of those Q's to find the strength of the field. We took that FQ and we divided it by the charge being brought into the field to get the strength of our field. This was also a vector. And by doing that then, we ended up with a second equation for a field by plugging KQQ over R squared in here. And 1Q cancels, so we get KQ over R squared, right? So those were our 3 equations. So now today, we just did EQ is, this is also a vector, sorry, equals KQQ over R, and this is a scalar. But now we're going to do exactly what we did with force, and we're going to divide this EQ by Q. We're going to divide it by Q to get rid of the one being brought in. So this little guy is brought in, the guy on the bottom, and the one on the top is the source. So when I do this, then it becomes KQQ over R divided by Q. And 1Q is going to cancel. And so I'm going to, notice I didn't put what's equal to over here. And so I'm going to be left with the second equation, which will be KQ over R. Now, what is this that we're finding? Well, the time's going to run out on this video. But let's think about it. Energy, and I didn't say it up here, but energy is measured in joules. So this is joules per coulomb.